Hello, this is Jack Jackson again, and we're going to be looking at approximating a definite integral from a graph. So the idea here is we have some function, say f of x, and we have its graph, for example, like this picture here. Oops. And here we want to integrate the function from -2 to 2. Let's get where we can see the graph here. Okay, good. And so if you see what we're doing, here's -2 here on x, here's 2 on x, so we're going between those two x values. And we're looking at areas under this curve. So there's a little area right here that's above the x-axis and below the curve. And then there's an area right in here that's above the x-axis and below the curve. So those are going to add to the integral, those areas. And from that we're going to subtract the area down here that's below the x-axis and above the curve, and this little area right over here which is below the x-axis and above the curve. So these two areas, this little bitty one here, the bigger one here, minus this one and this one. Okay. So how are we going to go at doing this? How do we approach this? Well, there's actually several different ways we could go at this. One way that would make sense, in theory at least, would be we could just count little rectangles. So after all, an area is how many little square tiles that you can fit inside of the area. So for example, this little rectangle right here is 1/2 wide by 1 tall. Okay, so notice the scale, different vertical and horizontal scales here. So that, see, 1/2 times 1, that's a half. So each one of these little rectangles has an area half. We could add those up, 1/2, 1, 1.5, 2, and so forth. The problem with that, in practice, is it becomes very difficult to look at, say, this little rectangle right here, and we only got a portion of it. Well, what portion of that rectangle did we get? That turns out to be a lot more difficult to estimate just by looking at it. So, of course, the other way we could do it is the way we've been doing things here with approximating this, is approximating with Riemann sums. So we can draw some rectangle here. Okay, and let me see if I can kind of illustrate this a little bit. Let me insert a rectangle, and let's say, okay, so here's a rectangle, let's say on this one piece. Let me make that where you can see through it a little bit. Okay, so we can see inside of it now. So what we want to do is we want to choose this. Now we could choose the height to be at the left end, or we could choose it at the right end, or we could try to find the height where the midpoint touches the graph. But really, if we choose it, we can choose it anywhere we want. Say, for example, if we choose here, though, notice that we're over by this much, right here, this little area that's inside the rectangle but outside the area we're trying to approximate, and we're under by this amount here. So clearly we're too high. Well, if we go down here, we're clearly too low because we're over by this amount right here, but under by a much bigger amount here. So what we want to try to do is to not necessarily go left, right, or midpoint, but try to go for the average height. So just try to go through here and balance as visually as best you can where these two areas are matching to each other. Usually the midpoint's going to be pretty good estimate, so you can kind of start there and then go up or down from there as needed. Looks like this is a little bit bigger than that, so I might want to come down a little bit. Okay. And so maybe there, okay, maybe that's the right one. Maybe we need to adjust a little bit. But the idea is to balance these two areas, the area that it's over one place and under the other place, so that those things balance out. If we could do that perfectly, then we would have exactly the right rectangle for that little piece. And we can do that on a bunch of pieces. We actually can get a pretty good estimate for that. So here's what I'm going to ask you to do, is to maybe look at this on your screen and go through here and try to figure out what you would come up with for the estimate here, and then we're going to test it against what I came up with here in a few minutes. Okay? So go ahead and do this on your own and come back. Press pause now. Well, I've asked you to come here and try to make rectangles over each interval. We know the widths of the rectangles, okay, are a half if we go with the grid lines here like I did here. And we just have to estimate the heights. It's much easier to estimate a height than it is an area. We want to try to balance these areas visually and then estimate the height visually. We know the width. Once we know the height, we can actually multiply the height by the width to get an area. Since the widths are all the same, we can factor that out and just add up the heights. Some positives, some negatives, so it's not really just heights, but actually y values that we're adding up. So when I did that, here's what I came up with. I decided to go ahead and use 8 rectangles. Okay. One seems to be missing right there. Okay. So let's see if we can get it back where it goes. Okay, so on a line. So I want to line this up so that it's on the x-axis at the top, and then I want to go up or down. Okay, it's too far down, there's too much over here and under here. Okay, go up. Okay, that's too far the other way. Somewhere in here we want to balance this out. Okay, down a little bit. Okay, that looks like that's kind of close, maybe a little bit more. And we can balance that out. That looks maybe okay. So those two areas, this one, this little, almost a triangle looking shape here, and this one down here, those are about the same size. And we do that on each one. So if you look here, we can see this, we want to try to balance this area right here with this one right here, this area in here with this one here, this little area here with this little piece here, this little unshaded piece with this piece here that's shaded in, this one that's the little unshaded piece here and the piece right there, and so forth. This one you got two little pieces sticking out here and one little piece underneath. So for example, here's one where the midpoint would have been too high. Okay, and balance those. So try to balance those out as best you can. Now once we've done that, we know the widths of all these are a half because we're assuming we're going straight on the grid lines. Then what we do is we go and find those y values. We can factor out the 1/2 and add up just the y values, then multiply by the 1/2 at the end. And so we go through here and we try to estimate, well, let's see, if this is -1, that may be -0.5 or something like that. And then what would this be? And so forth. And so here's the numbers I came up with for that. So I said this first one was about -0.6, and the next one was, there's -5, there's -6, so I said -5.8. So I tried to get to the nearest tenth best I could. This one looks like it's negative, let's see, -7.5, that's this one right here, -5.8 for that one, -2.8 for this one. This one I said was about 4.6. This one here I said was about 7.8. So there's 5, 6, 7, 8, about 7.8. The next one is 3.3. The next one is 6.0 negative. Add those up, you get -7. Half of that is -3.5. And so that is our estimate of the integral. And actually I've tried this with classes of students, and it actually works out pretty amazingly well. Some students can, they'll be over or under on a particular one a little bit of what it really should be, but by the time you do the whole thing, most of the students can get quite close to the correct answer using this method. So we're using Riemann sums, but we're trying to hit the average value. Here is the same function graphed in Graphmatica, and it tells us to, we're integrating it using the built-in Simpson's rule calculator. And of course, again, it's taking this area right here and this one here minus the one down here and down here. Notice there's more area below the x-axis than there is above, so we end up with a negative final answer. And to several decimal places, it's negative 3.51474. So our negative 3.5 was right on for 2 digits, 2 significant digits, 1 decimal place. So notice we can get a pretty accurate answer like that, and that works out pretty nicely.